Okay, in this video, I want to talk about it's somewhat technical, or well, let me say it like this. I want to talk about a result which is of great interest to people who are interested in the theory of differential equations. That means people like me who are pure mathematicians who get worried when we're dealing with differential equations like, is there really a solution to this? And to what extent is such a solution unique, right? This is something that really motivates quite a lot of theory of differential equations. But I think it's at least important to say some words about it, just because this might be something which impinges on some of the work that the people who apply the theory of differential equations, like the physicists and the engineers of the world, they might be interested in this as well, as it happens. Anyway, yeah, but that's, well, whatever. I don't need to. I don't need to denigrate anybody here, but yeah. Let's take a look at two situations here. And this is, again, pictures from your textbook. Here's the slope field for y prime equals 1 over x. And hopefully you understand that there's something a little bit pathological about this slope field. Because when x is equal to 0, this slope field is undefined. You cannot divide by 0. So 1 over x makes no sense if x is 0. And indeed, you see that along this vertical line here, there are no blue line segments because the slope field must be undefined there. So in particular, none of your solutions to this differential, there are no, yeah, right, so let me say it like this. In particular, there are no integral solutions, no integral curves which pass through a point on the y-axis. Because such a curve would have to have an x coordinate of 0 at some point, at that point where it crosses the x-axis, and then the derivative would be undefined. Yeah. So there are no integral curves corresponding to points along this y-axis here. Okay. Second point, looking at this example here, do you notice that there are, in fact, two solutions to this differential equation which pass through the point 0, 0? What that means is that there are two solutions, just as written here, there are two solutions to this slope field satisfying the initial condition y of 0 is equal to 0. So if your hope, which is a good hope to have, is that anytime you specify a differential equation together with an initial condition, that you would, one, have some solution, that's existence of solution, and then that solution would be unique. Well, unfortunately, that's simply not the case. And you can look in the textbook here for details about this particular pathological situation. But for us, I want to sort of state the theorem which gives us precise conditions to know when a solution exists and when it is unique. It's called Picard's theorem. Maybe you know, if you have any taste, you know about Captain Jean-Luc Picard. But maybe you also know that Captain Jean-Luc Picard doesn't exist. He's a figment of some human beings' imagination. Okay, so this is not the Picard who's the captain of the USS Enterprise, NCC 1701-D. Picard's theorem on existence and uniqueness. Of solutions to the first order equation y prime equals f of xy. So here is the statement. If you have f of xy having some properties, then you're guaranteed the existence and uniqueness of solutions to an initial value problem. Let me show you what those conditions are. If f of xy is continuous, so this is the first thing. I should say continuous at the point x naught, y naught. Okay, and you have that partial f partial y exists and is continuous. Again, at the same point. If you have these two conditions, then there exists a solution to y prime equals f of x, y with initial condition y of x naught equals y naught. Okay, you get a solution. You're guaranteed a solution to this differential equation. There is a little caveat that the solution may not be defined for all x, but at least it's defined in a small neighborhood of x. X naught, I should say. Neighborhood of x naught. All right, so you might not be able to have a full-blown solution for all that works for all x, but at the very least you get something local. Okay? And this is Picard's theorem, and this is, you know, about as good as it gets for this sort of thing. So just as an example of the one type of way that you might think about this result here, think about the following differential equation. Let's say that we're just given y prime equals xy, okay, and we're given an initial condition y of 0 is equal to 0. All right. Now, this function, if we view it as this function right here, xy, this is what's playing the role of our f of xy. This is as nice as can be, right? This function. It's a polynomial in two variables, right? So it's continuous everywhere. It's got partial derivatives for days. Those partial derivatives are themselves continuous everywhere, okay? So you are guaranteed a solution to this differential equation. And not only that, you are guaranteed that this solution is unique. Picard's theorem guarantees a solution. And in fact, it guarantees a unique solution to this IVP, initial value problem. Okay? Now, contrast that with the following example. Let's say that we were dealing with the differential equation y prime equals x over x squared minus 1. And let's say that I give you the initial condition that y of 1 is equal to 0. Well, this is absolutely unacceptable. Why? Because 1, when plugged into this expression here, well, it makes it undefined, right? So if this is what's playing the role of our f of xy right here, this is what's playing the role of our f of xy, note that this function is not continuous at the point 1 comma 0, because it's not even defined there, right? So there is no solution to this differential equation here. So that's the conclusion we can make here. There is no solution to this differential. Sorry, this I shouldn't say differential equation. I should say initial value problem. And that's precisely because x equal to 1 makes this thing undefined. Yeah? Okay. Well, we already talked about a situation in which you can have the function being, the slope field being defined everywhere, even continuous everywhere, but there is an issue around the uniqueness of solutions, right? This was the example, and we're not going to go into too much detail because this is pretty yucky. But if we have something like y prime equals the square root of the absolute value of y, okay, this is an autonomous equation, and you have the initial condition that y of 0 is 0, then solutions exist. But they are not unique. And we saw the slope field earlier. Okay. All right. All right. That's enough for this. And it's important that we understand when solutions exist and when they're unique. It's something that's probably of greater importance to people who care deeply about the theory of differential equations. But at least we can say that we did it. Okay. All right. Very good. That's all for this one. See you in the next one.